Okay, welcome you all for today's video. This is the last video of this thermodynamics lesson series. So today I will explain the second law of thermodynamics and the theory of entropy and Gibbs energy. After that I will explain a little bit of the heat engine and Joule-Thompson effect. So this may be the last session in this advanced thermodynamics part. ඉතින් මේක තමයි මම අද කරන thermodynamics වලට කරන අන්තිම වීඩියෝ එක advanced thermodynamics වල second වීඩියෝ එකේ කියන්නේ series එක මෙතනින් ඉවර කරනවා. තාපගත විද්‍යාවේ දෙවෙනි නියමය ඒත් එක්කම entropy, Gibbs ශක්තිය, Joule-Thompson ආචරණය සහ තාප එන්ජිම යන කරුණු ටික මම අද කතා කරනවා. ඉතින් මේ වීඩියෝ series එක එතනින් ඉවරයි. ඉතින් මාත් එක්ක රැඳෙලා ඉන්න කියලා ආරාධනා කරනවා. මේ වීඩියෝ ටික පුළුවන් නම් share කරන්න. පුළුවන් මගේ channel එක subscribe කරන්න. I am Hasanka Kalungarachi. Okay, let's go to the video. Okay. Yesterday, in last video, I explained the first law of thermodynamics, which was du equal dq plus dw plus dw dash. Okay, however this is non-expansion work other than expansion work. ප්‍රසාරණ කාර්යය හැර අනිත් කාර්යයන්ට තමයි අපි dw dash කිව්වේ. dw dash mean expansion work, ප්‍රසාරණ කාර්යය, dq mean heat change and du means internal energy. So you wanted to know that in an isolated system, if you consider isolated නැත්නම් ඒකලිත පද්ධතියක් ගත්තොත් ඒකේ අභ්‍යන්තර ශක්තිය නියතයි. We know that. And the first law of thermodynamics was explained, the energy cannot be created or destroyed. අපි ඒක කතා කරා ශක්ති සංස්ථිති නියමය වගේමයි තාපගත විද්‍යාවේ පළමු නියමය. Okay, today I am going to explain the theory of second law of thermodynamics. Second law of thermodynamics explain these typical things. First one is whether the reaction is or whether the processes whether they are spontaneous or not. ස්වයංසිද්ධයිද or non-spontaneous. Second law of thermodynamics explain whether the process will be spontaneous or not. ස්වයංසිද්ධයිද නැද්ද කියන එක කියන්න මොකක් හරි ක්‍රියාවලියක් ස්වයංසිද්ධව සිද්ධ වෙනවද නැත්නම් එහෙම නොවේද කියන්න කතා කරන එකක්. Second conclusion of second law of thermodynamics, it will discuss whether the whether a particular process, whether it will be reversible or not. Particular process reversible or not. Same as previous, but this is spontaneous or not, reversible or not. Those are the major conclusions we can obtain from this second law of thermodynamics. There is I couldn't found any direct expression for or definition for second law of thermodynamics, but it will discuss or it will conclude whether a particular process, whether it is spontaneous or not, non-spontaneous. ස්වයංසිද්ධ වෙනවද නැද්ද? Whether it is reversible or not. Likewise, there are two major conclusions we can get from this second law of thermodynamics. Okay. To get a clear idea, I will explain it as like this. Imagine there is a hot object. Hot object. It's better I use it red color to indicate hot. Hot means temperature is very higher. Okay. There is a cold object also. cold object also. Cold mean temperature is lower than hot objects. So if we connect these two objects by using a wire, metal rod or something, metallic compound, metal rod or wire, what will happen? අපි මේ දෙන්න දැන් උෂ්ණත්වය වැඩි වස්තුවක් සහ උෂ්ණත්වය අඩු වස්තුවක් ඉන්නවා. අපි මේ දෙන්නව මොකක් හරි ලෝහයකින් මේ සම්බන්ධ කරොත් රොඩ් එකකින් මෙටල් රොඩ් එකකින් වගේ මොකද වෙන්නේ? What will happen? Higher temperature mean higher heat. Q is higher. Lower temperature mean Q is somewhat lower. What will happen? We know that heat will transfer from higher temperatures to lower temperatures. අපි දන්නවා උෂ්ණත්වය වැඩි තැන ඉඳලා අඩු තැනට තමයි තාපය ගමන් කරන්නේ. එහෙනම් heat will transfer from hot object to cold object. That is natural thing. It is happening in naturally. නේද? ඒක සාමාන්‍ය ස්වයංසිද්ධ අපි ගිනි මැලයක් ගාවට ගිහලා අපි ඉන්නකොට ගිනි මැලේ ගාව රස්නිය වැඩි, අපි ගාව රස්නිය අඩුයි. අපිට ටිකක් වෙනකොට රස්නිය දැනෙනවා. ඒ කියන්නේ මොකද්ද? උෂ්ණත්වයේ වැඩි තැන ඉඳලා අඩු තැනට තමයි තාපය ගමන් කරන්නේ. ඒ වගේ මෙතෙන්දිත් තාපය ගමන් කරන්නේ වැඩි තැන ඉඳලා අඩු තැනට. ඉතින් here heat transfer from higher temperature object towards lower temperature object. So this heat transfer is happening naturally. මේක සිද්ධ වෙන්නේ ස්වභාවිකව. So to this process, natural process, we call this is spontaneous. From higher temperature to lower temperature, heat will transfer. That will happen naturally. So we call that spontaneous. ඒක ස්වයං සිද්ධව සිද්ධ වෙනවා කියලා අපි කියනවා. So this is an example for spontaneous process. How about this? One object here, one object here. Here temperature is T1, here also T1, same temperature. We connect by wire. What will happen? Heat energy transfer from here and here, both are same. So this will be a reversible process. Okay, likewise. So my main target was this, to explain what is spontaneous. However, what about this? Here your cold object, here your hot object. Higher temperature and lower temperature. Is it possible heat transfer from cold object to hot object naturally? අයිස් වල ඉඳලා ඒ කියන්නේ උෂ්ණත්වය අඩු තැනක ඉඳලා වැඩි තැනකට තාපය ගමන් කිරීමක් කියලා කොහෙවත් අහලා තියෙනවද ඔයාලා? නෑ. කවදාවත් never happen this thing in naturally. ස්වභාවිකව කවදාවත් there is no any heat transfer from cold object to hot object. That will not happen naturally. මේ වගේ ඒවාට අපි කියනවා non spontaneous. However, to happen this process, this non spontaneous process to happen, මේක වෙන්න නම් මොකක්ද අපි කරන්න ඕන? We have to provide energy. We have to provide energy, or we have to pump energy to fulfill this process. Non-spontaneous, naturally this is not happening, but if we provide excess energy, we can do this thing also. However, it is non-spontaneous. Okay, spontaneous means it will happen naturally. Okay, I think you may got the point. Another example. Here there is a waterfall. Water always will come from the top to bottom. Always flows top to the bottom, not opposite direction. You can understand. So this water flowing spontaneously. You can understand. However, water will not go from bottom to top. Opposite direction will not happen in naturally. However, if we provide energy by using a motor, if we use a pump, we can provide energy via pump, electrical energy. We can do this non-spontaneous process. However, non-spontaneous means it is not happening naturally. To get that thing, we can provide excess energy. So, spontaneous means naturally happening, non-spontaneous means it won't happen naturally. Okay. Another example, if I explain you, I think this is sufficient. We have very limited time. Okay. Spontaneous and non-spontaneous, I think you may understand now. Okay. I will erase everything. Another thing we have to, we can get from this equation or second law, if it is spontaneous, if spontaneous or swansiddhainam, it will always increase the disorder. මොකද කියන්නේ මොකක් හරි දෙයක් ස්වයන් සිද්ධ වෙනවයි කියන්නේ ඒක වෙන්නේ ස්වයන් සිද්ධයි නම් ඒක වෙන්නේ කොයි පැත්තටද අපිලිවෙල වැඩි වෙන පැත්තට අපිලිවෙල වැඩි වෙනවා ස්වයන් සිද්ධ ක්‍රියාවලදී අපිලිවෙල වැඩි වෙනවා. So if it is spontaneous, it will increase the disorder. අපිලිවෙල වැඩි කරනවා. So to indicate this disorder, we use another thermodynamic function property called S or entropy. මොකද්ද? If a process is spontaneous, it will goes towards increasing disorder. Disorder එක වැඩි කරන පැත්තට තමයි සිද්ධ වෙන්නේ. මේ disorder එක, to indicate the disorder, we use a new function or new thermodynamic property or new state property, state or thermodynamic property නැත්නම් අවස්ථා ගුණයක් හෝ තාපගතික ගුණයක් මොකද්ද entropy කියලා එකක් හඳුන්වනවා. Okay. If a process is spontaneous, this S entropy also a thermodynamic property, මේක තාපගතික ගුණයක් entropy කියන්නේ, that means it is depend on the initial state and final state. So if we get a process A goes to B, this is a process, it is spontaneous. Here initial entropy is S1, final entropy is S2. What will be the total change of entropy? To get that, we can deduct S1 by, we have to deduct initial entropy by final entropy S2. S2 minus S2 mean, S1 mean delta S. Delta S mean change of entropy because it is a state property, not a path property. State property, we can get the change of state properties by deducting lower or initial value from final value. So final value is S2, initial value is S1, we can obtain delta S. Okay. If it is a spontaneous process, the delta S entropy change should be always less than higher than zero. So if a process is spontaneous, the disorder or entropy should be higher than 0. That means it should be a positive value. So in spontaneous reactions or spontaneous processes ස්වයංසිද්ධ ක්‍රියාවලිය වලදී එන්ට්‍රොපිය හැම වෙලේම බිඳුවට වඩා විශාල විය යුතුමයි. මෙහෙම එකක් දීලා තිබ්බොත් ඩෙල්ටා S බිඳුවට වඩා විශාලයි කියලා මේකෙන් කියවෙන්නේ මේක ස්වයංසිද්ධ ක්‍රියාවලියක්. This is a spontaneous process. That's the meaning of this. Delta S is higher than 0. It is positive. Okay. So there are another things, no? What? I think you may got the point. Okay. Okay. Now, if delta S is less than 0, delta S බිඳුවට වඩා කුඩයි නම් මොකද වෙන්නේ? So value will be negative. That will be non-spontaneous. එහෙනම් මේක ස්වයංසිද්ධ ක්‍රියාවක් නෙමෙයි. කොහේ හරි delta S බිඳුවට වඩා අඩුයි කියලා දීලා තිබ්බොත් ඍණාගයක් නම් එයා ස්වයංසිද්ධ ක්‍රියාවලියක් නෙමෙයි. This is spontaneous. How about this? Delta S equal 0. If delta S equals 0, what is that? It is the thing, the reaction is or process is reversible. Reaction will happen towards both directions. That means it is reversible if the delta S is 0. Here delta S is larger than 0, that is spontaneous, value is positive. If the delta is less than 0, that means it is negative, it is non-spontaneous. If the delta is equal 0, that means it is reversible. However, is it possible? This delta is equal 0. Is it possible? Reversible? No, actually this expression is used for ideal gases in ideal conditions. However, in real situations, the thing will be this. Reality is this. Delta S should be larger than 0. That's the reality for real conditions or real gases or real liquids. Likewise, in ideal cases, delta S equal 0. We can use that expression. Keep that in your mind. Okay. Now, I will explain this spontaneous thing. Imagine I have a glass bottle. It's on the edge of a desk. Accidentally it will fall down and it will glass brittle, so it will be break into parts. Okay, now glass bottle was broken. However, is it happening in opposite direction? Will this broken parts will combine and form the new that previous bottle? Is it possible? Initially what happened? There is a good bottle, not broken. However, accidentally it will fall down and it broken into pieces. කැලි වලට කැඩුනා. ඒක ස්වයන් සිද්ධවම ආපස්සට ආයෙත් හැදෙනවද? ඒ කැලි එකතු වෙලා බෝතලේ හැදෙනවද? Is it possible? These broken pieces combine naturally and it will again form the original bottle. Is it possible in naturally? No. We have to get this every pieces and we have to melt it and again we have to make the bottle. After melting we have to supply energy නේද? මේක අලුතින් ආයේ බෝතලේ හදන්න නම් මොකද කරන්නේ? අපි මෙයා උණු කරලා glass උණු කරලා ආයෙත් අච්චුවකට දාලා මෙයාව හදාගන්න. ඒ කියන්නේ අපි ශක්තිය පිටින් දෙන්න ඕන. ඉතින් එහෙනම් this breaking of glass bottle is spontaneous, but rebuilding of glass bottle after broken, it is non-spontaneous. Okay, that's another example. Okay, however, what happened here? This bottle is one piece, one bottle, no, one piece. After spontaneous process like breaking, it will make several parts. That means disorder will increase. තේරුණාද? බෝතලේ තිබ්බහම තනි විදිහට තිබ්බොත් බෝතලේ එක බෝතලයයි. එක කෑල්ලයිනේ. කෑලි කීපයක් නැනේ. එක බෝතලේ තනි බෝතලයක් තියෙන්නේ. එයා කැඩුනට පස්සේ මොකද වෙන්නේ? කෑලි කීපයකට කැඩෙනවා. ඒ කියන්නේ එයාගේ අපිලිවල මොකද වෙන්නේ? වැඩි වෙනවා. එක කෑල්ල මුලින් හිටිය එකයි දැන් කීප දෙනෙකුට කැඩිලා. ඒ කියන්නේ අපිලිවල වැඩි වෙනවා. ස්වයං සිද්ධ ක්‍රියාවලියකදී අන්තිමේදී හැදෙන කෙනාගේ අපිලිවල සාමාන්‍යයෙන් වැඩි. ඒක තමයි ස්වභාවික වෙන දේ. ඒක මතක තියාගන්න. Okay. I think you may got the point again. Very clear. Okay. Okay. Now here onwards, මෙතනින් එහාට we are talking about the entropy. Okay. The common equation for entropy ds, change of entropy, is equal dq, here reversible, over T. This is the common expression for enthalpy change. If we don't considering the change, S equal Q reversible divided by T. This is for this equal mark mean. I told you equal mean always it is reversible. If it is delta S like S, likewise this. If you write down this equation, delta S is larger than this function. That means delta S is larger. That means this is spontaneous. However, if they given delta S is less than Q over T, that means delta S is less than mean it is negative. So this is non-spontaneous, this is spontaneous, and this is reversible. Okay, here onwards we use this equation. This is the common expression for entropy at reversible condition, reversible system. It is reversible with the environment. Okay, so we are using this equation further. Okay, this is the common equation. If it is equal sign, there should be reversible mark also. Keep that in your mind. Okay. So, likewise, previous video we talked about the first law of thermodynamics. We got the equation for first law and we played with that equation. We changed the conditions: adiabatic, isothermal, isochoric. There are so many conditions now: isobaric, isochoric, isothermal, and diabatic. Likewise, we changed several conditions. Likewise, here we have to change the condition and we will see what will happen to this equation. That's the thing. Okay. Okay. Now I will explain you to go further. First of all, I have to say one thing. In last video I told you U, internal energy, is a function of V and T, and enthalpy is a function of P and T. Okay. Yesterday we discussed that. However, you have to remember that these equations are for real situations. තාත්වික අවස්ථාව, තාත්වික වායු ගැන කතා කරද්දී තමයි මේක පාවිච්චි කරන්නේ. However, when we are talking about ideal gases, V and P will not affect for internal energy and enthalpy of ideal gases. Okay. At that time when we are using ideal conditions, this will be simplified as U equal function of T and H equal function of T. In ideal conditions, these above expressions are simplified as like this, because in ideal conditions there is no any intermolecular forces. Because of that, no pressure build up, and we assume in ideal conditions the volume is negligible of that ideal gases. So So because of that, volume also negligible. So only factor is temperature in ideal conditions. Keep in mind, for real gases නැත්නම් තාත්වික වායු වලදී අපි දන්නවා පරිමාව සහ පීඩනය කියනවා ඒවට අන්තරාණුකාකර්ෂණ බල තියෙන හින්දා පරිමාව පීඩනය වගේ දේවල් බලපානවා තාත්වික වායු වලට. ඒ වගේ අයට අපිට මේ අභ්‍යන්තර ශක්තිය V සහ T ගේ ශ්‍රිතයක් කියලා දුන්නා. එන්තැල්පිය P සහ T ගේ පීඩනය සහ උෂ්ණත්වයේ ශ්‍රිතයක් කියලා මම කලින් වීඩියෝ එකේ කතා කරා. හැබැයි ඒ කතා කරපු එක මතක තියාගන්න ඕන. ඒ සාමාන්‍ය තාත්වික වායු වලට. හැබැයි අතාත්වික නැත්නම් මේ අයිඩියල් ගෑසස් වලට පරිපූර්ණ වායු වලටදී පරිමාව සහ උෂ්ණ පීඩනය ගණන් ගන්නේ නැහැ. මොකද අපි සලකනවා පරිපූර්ණ වායු වල පරිමාව ශුන්‍යයි. ගණන් ගන්න බැරි තරම් නිග්ලිජිබල් කියලා. ඒ වගේ මේව අතර අන්තරාණුක ආකර්ෂණ බල නැහැ කියලා උපකල්පනය කරනවා. එයාලා අතර අන්තරාණුක ආකර්ෂණ බල නැහැ කියන්නේ පීඩනයක් ගොඩ නැගෙන්නෙත් නැහැ. ඉතින් ඒ නිසා පරිමාවකුත් නැහැනේ. ඒ නිසා පරිමාව සහ පීඩන යන පද දෙක මේ අපේ පරිපූර්ණ වායු වලදී ගණන් ගන්නේ නැහැ. එතකොට මේ සමීකරණය මේ විදිහට සුළු වීමකට ලක් වෙනවා. ඒකත් මතක තියාගන්න. ෂෝට් නෝට් එකේ ගහ ගන්න ගමන් ඔක ලියා ගන්න. මට ඒක ඊයේ කියන්න අමතක වෙච්ච දෙයක්. Okay. Now, what is the relationship between internal energy and enthalpy? මොකක්ද අභ්‍යන්තර ශක්තිය සහ enthalpy සම්බන්ධකම? We know that U is equal H plus PV. For change, delta U equal delta H plus delta PV. Okay. What about isothermal conditions? If we apply isothermal conditions, so in these equations, I wanted to say that this is our relationship between H and U, but just keep in mind that I wanted to say another thing. Delta U and delta H, what about them in isothermal conditions? If we apply isothermal means සමෝෂ්ණ. සමෝෂ්ණයි නම් මේවා මොකද වෙන්නේ? If you carefully write down or understood last thermodynamic session, you will remember what are the common expressions for du and dh. What is du mean? Cv dt. Delta H mean Cp dt. Another expression ncvm dt. Here ncpm dt likewise. Anyhow, here dt expression is here dt dt. What is the point? In isothermal mean temperature change is 0, dt is 0. So du delta U is equal Cv dt mean dt is 0, so expression will be 0. At isothermal conditions, delta U equals 0, also delta H also 0. Keep in mind. Okay. If we consider the first law of thermodynamics, delta U is equal or du is equal dq plus dw. Okay. If we consider reversible conditions, if it is reversible process, what will happen? If it is a reversible process, du is equal dq reversible plus dw reversible. We assume this is a reversible process. Okay. So du equal dq reversible plus dw reversible. Okay. So what is the simplified version? If it is reversible, this is the expression. Now we will assume this process is reversible and this is isothermal. dt is 0. What will happen? At that time du will be 0. I discuss here. 0 equal dq reversible plus dw reversible. So we will get an expression dq is equal dw minus dw reversible. Okay, now we got the our useful equation. Okay, now how can we simplify this equation? Here dw mean, here first of all I must say this is first law of thermodynamics, there should be a dw dash thing, non-expansion work. I assume here non-expansion work is 0. After that I get this equation, please keep in mind. Okay, however here dw mean expansion work. Expansion work mean minus Pex dv, expansion work. Okay, I will substitute that expression for here. dq reversible is equal, here minus sign, okay, bracket, this minus sign is anything other thing, no? This dw mean expansion work, minus is another thing. Okay, minus, now dw in minus Pex dv. Okay, now initially we assume this is a reversible process. Reversible mean system is in a equilibrium with the surrounding, so that means Pex equal P system. So P system equal Pex external equal P. I get a common pressure expression minus P dv. Okay, dq reversible. Okay, now minus minus will be plus P dv. Okay, now how can we simplify? If we assume this is an ideal gas, if we assume this is an ideal gas, this PV equal nRT, P will be nRT divided by V. So I substitute that thing here, dq reversible equal nRT divided by V dt. Okay, I substituted this obtained equation at ideal conditions. ඔයාලට තේරුණා නේද ළමයි? මම ඔහේ කියන්න ඉංග්‍රීසි වලින් මොකද්ද කරේ? මේ තාපගත විද්‍යාව පළමු නියමයේ දැම්මා. dw dash කියන්නේ ප්‍රසාරණ කාර්යය හැර අනිත් කාර්යයන්නේ. ඒ කාර්යයන් බිඳුවයි කියලා සලකලා සමීකරණය මේ විදිහට සුළු කරගත්තා. මම මේක ප්‍රතිවර්තී නැත්නම් මේ දෙපැත්තටම සිද්ධ වෙන ප්‍රත්‍යාවර්තී ප්‍රතික්‍රියාවක් නැත්නම් ක්‍රියාවලියක් කියලා උපකල්පනය කරාට පස්සේ dq reversible සහ dw reversible කියලා දැම්මා. ඒකල මම උපකල්පනයක් කරා මේක සමෝෂ්ණයි කියලා. සමෝෂ්ණයි කියන්නේ ඩෙල්ටා t බිඳුවයි. උෂ්ණත්ව වෙනසක් වෙන්නේ නැහැ. ඒ උෂ්ණත්වයේ බිඳුවයි නම් අපි ඊයේ ගත්ත ඉක්වේෂන් එකක් අපි තමයි u සහ h සහ දෙකටම අපි ගත්ත එකක් cv dt කියලා. මේකට ගත්ත cp dt කියලා. දෙකේම උෂ්ණත්ව වෙනසක් තියෙනවානේ. උෂ්ණත්ව වෙනස බිඳුවයි නම් මෙයාලත් බිඳුව වෙනවා. ඉතින් ඒ අවස්ථාවේදී මෙයා බිඳුවක් වුණා. ඊට පස්සේ මම මේක මේ dw කියන එක න සමීකරණ එහා පැත්තට අරන් ගියා. එතකොට එයා ඍණ වුණා. මේ විදිහට පදයක් ගත්තා. ඊට පස්සේ මෙයා මුලදීම උපකල්පනය කරා මෙයා රිවර්සිබල් නැත්නම් ප්‍රත්‍යාවර්තී නම් බාහිර පීඩනයයි අභ්‍යන්තර පීඩනයයි පද්ධතිය සමානයි. ඒ වුණාට පොදු පීඩනය කියලා පදයක් මම දාගත්තා. මෙතන ඍණයි මෙතන ඍණයි ධන වුණා. මේ පීඩනය p කියලා දාගත්තා. දැන් මෙයා අයිඩියල් ගෑස් එකක් කියලා පරිපූර්ණ වායුවක් කියලා උපකල්පනය කරාට පස්සේ ඒ වුණාට PV සමාන nRT සමීකරණය දාගන්න පුළුවන්. p යුක්ත කරගත්තට පදයක් ගත්තා. යා මම මෙතන දාගත්තා. හරිනේ. After that, now dt mean differential term, so we can differentiate this. No. There here should be dv, no dv. I'm sorry, dv. dv mean differential of v. Here volume is as the denominator. So I will simplify this. dq reversible equal n is constant. However, first of all we have to put integral marks. Okay, here n and r also constant. On the other hand, we assumed isothermal temperature is not changing, it is constant. T also constant. Now 1 over V dV. Okay, we got this expression. This integration of this Q dq 1 integrated by dq, we get Q reversible equal here nRT, here 1 over V integrated by dV, it will be ln V. However, we have to apply limits, initial volume to final volume, V1, V2. Initial volume we have to put at the bottom of integral mark, and final volume will be top of the integral mark. So here we have to apply limits, brackets, V1, V2. Now we have to simplify. Q reversible is equal nRT ln V, that means ln V2. We substitute this V2 instead of Vn. To simplify this limits සුළු කරන්නේ කොහොමද? ඉහළ සීමාවෙන් පහළ සීමාව අඩු කරනවා. ඉහළ සීමාව මුලින්ම V වෙනුවට ආදේශ කරනවා, ඒකෙන් අඩු කරනවා පහළ සීමාව ඒකට ආදේශ කරලා. Initially I substitute V2 as ln V, ln V2 minus, next I will substitute V1 as ln V, ln V1. Q reversible equal nRT. Here ln V2 minus ln V1 ලඝු ගණක නීති වලට අනුව, this is deduction, we can express as a division. බෙදීමක් විදිහට දාන්න පුළුවන් ලඝු ගණකවලදී. ln V2 බෙදීම V1. So we got this expression. Now we can simplify this. කොහොමද අපි මේක තව සුළු කරගන්නේ? This t, if we divide both sides by t, we will get Q reversible over t equal nR ln V2 divided by V1. What is this? Q reversible බෙදීම t divided by t, that mean Q reversible over t, that mean entropy. So here we got the expression for entropy. Okay. So here if you consider change dq reversible, this will be the entropy. Entropy change ds equal nR ln V2 divided by V1. This is a expression for entropy. Okay, මේක තෘප්ත කරගන්න ඔයාලා දැනගන්න ඕන. Okay, so we know obviously one thing, another thing according to Boyle's law, V1 divided by V2, P1 V1 equal P2 V2, V2 divided by V1 equal P1 divided by P2. So instead of this equation we can use also ds equal nR ln P1 divided by P2. This is for a small change. If we consider large change, we can put delta S equal nR ln P1 divided by P2 or V2 divided by V1 likewise. Okay. Okay. This is one conditions, one or two conditions: reversible, isothermal. Okay, and we will move to next conditions. Okay. I think now you may familiar with these calculations. All are same, few theories and same calculations. Okay. Now I will introduce you adiabatic conditions. Adiabatic means ස්ථිරතාපී. ස්ථිරතාපී නම් dq is equal to 0. Okay. Now dq, if dq is 0, what is the common expression for delta s? Delta s equal dq divided by dq reversible divided by t. If it is adiabatic, no doubts, dq will be 0, so delta s will be 0. Okay, there is nothing. Okay. Okay. Let's consider isochoric conditions. Isochoric conditions. So common expression for entropy, dS equal dqv, v mean isochoric, divided by T. Okay. Now we know in isochoric conditions, here du is equal in CVM dt. We know that, or CV dt. Likewise, we got this expression. Instead of this dqv, I can substitute here heat change in isochoric process mean du. So I can substitute this part also. NCVM dt, NCVM dt divided by T. Okay, now we will integrate. Okay. Now here 1 integrated by ds mean s equal. Here n and CVM are constant, we can get out of the integral mark. Okay, now 1 over t integrated by dt mean, I told you in last video also, 1 over something, if 1 over x integrated by dx, answer will be ln x. Likewise here s equal n CVM ln t. However, we have to input limits t1 to t2. Here ln within brackets t1 to t2. Okay. How can we simplify this? We have to deduct lower limits by upper limits. උඩ සීමාවෙන් යට සීමාව අඩු කරන්න ඕන. s සමානයි ncvm වරහන් ඇතුලේ ln t2 minus ln t1. ලඝු නීතිය අනුව අප දන්නවා, as the log rules we know, minus deduction will be expressed as a division of logs. So s equal ncvm ln t2 divided by t1. This is expression for isochoric conditions. So if I include isobaric conditions or isobaric, this is isochoric. In isobaric mean ස්ථීර සමපීඩන. මෙයා සමපරිමා. Samapidana means dP will be 0. If we add a common equation for entropy is ds equal dq divided by T. Common expression in isochoric conditions, ds equal dq p divided by t. Okay, we know dh equal qp equal in cp dt, so cp dt or in cpm dt. Likewise, we can substitute this in cpm instead of this dqp. ds equal n cpm dt divided by t. Again, we have to integrate likewise here. So this is the final expression for isobaric conditions. So we have to always mention the conditions. So here S mean entropy, equal mean always this is reversible process. See, here we apply thermal capacity, molar thermal capacity or thermal capacity. We have to, if we introduce thermal capacity, the system should be homogeneous. Neither make a entropy නම් සමාන ලකුණක් තියෙනවා නම් මේක ප්‍රතිවර්තී වෙන්න ඕන, ප්‍රත්‍යාවර්තී ක්‍රියාවක් වෙන්න ඕන. මෙතන තාපදාරිතාවේ තියෙනවානේ. තාපදාරිතාව කියන්නේ මේක සමජාතීය මිශ්‍රණයක් වෙන්නත් ඕන. Yesterday we talked about that. අනිත් අතර in here isochoric conditions, and usually we use this equation for ideal gases and constant amount. There are 5 conditions නේ. මොනවාද එකක්? reversible process, and homogeneous, samajatiyai, here me isochoric, ideal gas, constant amount, nishchita ප්‍රමාණයක් තියෙනවා. මෙයාගේ in isobaric process, this equation is valid for reversible, homogeneous, because we are using thermal capacity term, homogeneous, and this is isobaric, and ideal gas, constant amount. So these are the conditions. We have to always, if we write down the equation, we have to always mention the conditions. Okay, I will erase these things. Okay, now we got another 2 major equations. If you can remember, entropy change is equal to dq divided by t, common expression. In isochoric conditions, සම පරිමාතත්වයටදී ds equal dqv divided by t, that means ds equal du divided by t. One major expression with last session's knowledge. On the other hand, in isobaric conditions, සම පීඩන තත්ත්වයටදී ds සමානයි dqp වෙනවා. Here t, dqp කියන්නේ අපි දන්නවා enthalpy ට, S equal dh divided by t. These are major expressions. Okay, so here instead of this, yesterday we learned du is equal dqv is equal cv dt equal ncvm dt. Now we got another expression for internal energy, that equal dST. Likewise, enthalpy is equal dQp equal Cp dt equal NCPm dt equal, now we got dH is equal dST. Here dST mean we have to input the here isobaric conditions, here here isochoric conditions, here ds at isobaric conditions, here isochoric conditions. Okay, these are the major things you have to keep in your mind. Okay, we talked about so many things, isochoric, isobaric, diabatic and isothermal conditions. Okay, now I am reaching to the end of second law calculations. Okay, there are some other one or two calculations. Okay, imagine first law of thermodynamics, du is equal dq plus dw. Okay, instead of this du, we know that du is equal cv dt and cvm dt also, and this dw is equal this is expansion work. We assume non-expansion work is 0. ප්‍රසාරණ කාර්ය හැර අනිත් කාර්යන් සිද්ධ වෙන්නේ නැහැ කියලා උපකල්පනය කරනවා. මොකද හැම වෙලේම තාපගත විද්‍යාවේ පළමු නියමයට කොටස් තුනක් එනවානේ. dq plus dw plus dw dash කියලා. dw dash mean non-expansion work. We always assume non-expansion work is 0. එහෙම තමයි අපි මේක ගන්නෙ. හොඳේ. හැම වෙලේම එහෙමයි ඈ. මම ඒක කිව්වේ නැහැ හැම වෙලේම. මොකද එහෙමයි ගන්නෙ. Here du is, we can substitute cv dt dq, we consider reversible conditions. Okay, here dw reversible, initial equation I write likewise this. Okay, now cv dt dq reversible, and instead of this dw I will substitute minus pex dv. Okay, now what can you say about this? Here we assume that this is reversible. When we are dealing with entropy, always we assume if there is a equal mark, that means this is reversible. If it is reversible, system is in an equilibrium with environment, that means Pex equal P system. P system equal P external. So here Cv dt, dq reversible, here minus Pex, instead of Pex I will use P, just P dv. Okay, instead of this P I will substitute PV equal, now we will consider this is ideal, another assumption, ideal gas. Ideal gas, PV equal nRT, P equal nRT divided by V. Substitute I, V dV, Cv dt equal dq reversible minus nRT divided by V, here dV. Okay, now I will rearrange this equation, because here dt and t term will be here. Okay, so I will rearrange the equation. I will divide every term by t. Okay, here t, t, t. Okay, t to t will be cancelled out. Here t. Now we got a familiar one. Who? This dq reversible divided by t. Who is that? That's the entropy. So here cv dt t, here entropy minus nr dv by v. Okay, now we got this equation. So I want an expression for ds, so I will rearrange the equation according to that. ds equal cv dt minus, now this minus will be plus nr dv by v. Okay, I got this equation. Now I can easily integrate. Here s equal cv is a constant, තවපදාර්ථතාවයේ නියතයක්, එයා එළියට ගත්තා. Here should be t, this t. Here 1 over t integrated by dt plus, here n and r also constant, nr integrate dv by v. Okay, how can we integrate this? S equal cv 1 over t dt integration mean ln t. However, we have to put here, I forgot that we have to put the limits of temperature, and here we have to put the limit of volume v1 to v2. v1 here t1 to t2 plus nr ln v v1 to v2, v1 to ln v v1 and v2 limits. We can simplify the limits by deducting lower limits by upper limit. ඉහළ සීමාවෙන් පහළ සීමාව අඩු කරනවා. S is equal cv ln t2 minus ln t1 plus nr ln v2 minus ln v1. Okay, now simplifying cv ln t2 minus ln t1 means ln t2 divided by t1 plus nr ln v2 minus ln v1 mean ln v2 divided by v1. I will get this common expression. This is another expression for change of, if we consider change of delta S, we can express this equation, use this equation. Okay. In example, sometimes they will given this equation, this final equation, and especially in final examination, if they will given this expression and they will ask how could you obtain this equation, you have to prove the obtain method. This method you have to write down these equations as you have to prove this equation. Okay, that's another thing. Okay, I will erase. Okay, I think we discussed everything about this enthalpy and entropy, and finally I will explain about Gibbs energy. We will little bit Gibbs energy. Gibbs energy gives an idea about whether it is spontaneous or not. We can calculate Gibbs energy. There is a equation. Gibbs energy is equal H minus Ts. if we consider change, delta G is equal delta H minus T delta S. This is a common expression for Gibbs energy calculations. Okay, we have to know that this Gibbs energy we always expression අපි මේ Gibbs ශක්තිය හැම වෙලේම මොකක් හරි එකක් ස්වයන් සිද්ධයිද නැද්ද process එකක් ස්වයන් සිද්ධද නැද්ද කියලා බලන්න තමයි use කරන්නේ. Gibbs energy ගේ equation එක තමයි මේක. මේ Gibbs energy එක අපි හැම වෙලේම use කරන්නේ under these conditions, under isothermal and isobaric. These are the conditions we are using delta G. So, අපි මේ Gibbs ශක්තිය හැම වෙලෙම යෝජනා කරන්නේ සමෝෂ්ණ සහ සමපීඩන තත්ත්වය යටතේදී තමයි අපි අර්ථ දක්වන්නේ Gibbs ශක්තිය. එතකොට Gibbs ශක්තිය කොහොමද එතකොට අපි ලියන්නේ delta G we indicate at T and P. T and P here subscript විදියට දාන්නේ මේවා constant කියලා තමයි පෙන්නන්නේ. So we express delta G Tp, that means isothermal and isobaric. සමෝෂ්ණ සහ සමපීඩන තත්ත්වයටදී තමයි Gibbs energy අර්ථ දක්වලා තියෙන්නේ. If the delta G Tp is 0, මෙයා බිඳුව වුණොත් මොකද්ද ළමයි එකෙන් කියන්නේ? මෙයා reversible process එකක්. නැත්නම් මෙයා ප්‍රත්‍යාවර්තී වෙනවා බිඳුව වුණොත්. If the delta G Tp is larger than 0, I will write erase these things. Larger than 0, that means it is positive value, that will be it is non-spontaneous. If the delta G Tp is less than 0, that means it is negative value, that means it is spontaneous. Okay, you have to remember these things. If the delta G Tp is positive value, it is non-spontaneous. ඒක ස්වයන් සිද්ධ නොවන එකක්. ස්වයන් සිද්ධ නොවේ. ප්‍රත්‍යාවර්තී වෙනවා බිඳුවට සමාන වුණොත් බිඳුවට වඩා අඩු නැත්නම් ඍණාගයක් આવුත් එයා ස්වයන් සිද්ධයි. You have to keep these in your mind. Now, if we consider entropy, if the delta S is equal 0, it is reversible, equal to Gibbs energy. 0, it is reversible. At delta S is higher than 0, means it is positive. Positive means it is spontaneous. In contrast to delta S, here delta GTP, it is positive, it means non-spontaneous. However, in delta S, it is positive, means it is spontaneous. You can see the difference. On the other hand, if the delta S is less than 0, that is negative value, means it is non-spontaneous. Okay, you have to keep these things in your mind. Okay, these are the summary of second law of thermodynamics. Okay. We talked about so many things. So here the major thing is entropy. Common equation for entropy change is equal ds equal dq reversible divided by temperature, not dt, it is temperature. If there is a term ds, if it is equal sign, equal mean always it is reversible. Reversible mean external pressure of the system is equal to system pressure. You can use PV equal nRT under ideal conditions. You have to remember these things and conditions. Okay. Okay, I will now everything you wanted to know about second law of thermodynamics, I explained. Let's move on to the applications of first law of thermodynamics, which is Joule-Thompson effect. Okay, let's talk about the Joule-Thompson effect. However, in this time I have to say, in 19th century, so many scientists believe some gases like hydrogen, oxygen, nitrogen type gases never liquefy. They argue because some gases can liquefy, they believe that, but hydrogen, nitrogen, oxygen type gases never liquefy. So they assume that if we increase the pressure up to 2000 bars, if we increase the pressure, gases will not liquefy. So, however, in those time period, Joule and Thomson's, both of them done research for this liquefaction phenomena to prove. They always argue gases, every gases can liquefy. So to prove that, they build up a procedure. What is that? Gases in higher temperatures and higher pressures, some gases, if we allow them to expand, gases in higher temperature and higher pressure, if we allow to expand them, ප්‍රසාරණය වෙන්න ඇරියොත් එහෙම මේ gases වල temperature will be low and temperature will decrease and pressure also will decrease. They observed that. What is that? Gases in higher temperature and higher pressures, if we allow these gases to expand, for expansion method, after expanding, temperature and pressure will be lower. Okay, this decreased temperature and pressure, decreased gas, again recycle to this system, again introduce this lower temperature and lower pressure gases, again introduced into this initial module, and again its temperature and pressure again will be lower. By doing this cycling procedure again and again, finally this gas will be liquefied. So they proved this. So this is the known as Joule-Thomson effect. Let's talk about that in proper manner. Okay. Imagine there is a cylinder. Okay. There is a cylinder. It is frictionless cylinder. ඝර්ෂණයක් නොමැති සිලින්ඩරයක් තියෙනවා. And it is thermal insulated. තාප පරිවාරක thermal insulated or insulation. තාප පරිවාරක මේ සිලින්ඩරයක් තියෙනවා. ඒ කියන්නේ තාපය එහා මෙහා යන්නේ නැහැ. ඒ කියන්නේ මේ ඇතුලේ සිස්ටම් එකේ temperature is heat is constant. තාප පරිවාරක thermal insulation. Okay. Here in the middle of the cylinder there is a porous plug. porous plug එකක් තියෙනවා, නැත්නම් සවිවර පේනුවක්. ඒ කියන්නේ මේකේ there are very small pores in this middle wall. Gases can go in between these two chambers, but the diffusion speed is very low. Gas මේ පැත්තේ තියෙන gas එකක් මේ පැත්තට යන්න පුළුවන්, හැබැයි very slow. rate එක හරිම slow එක යන මොකද මේ pores very tiny, very small pores are there. However, gas can go through them, but the rate is very slow. Okay. Imagine here there is a piston. This is a piston. Another piston is there on the this side. Initially it is attached to this porous plug. There is no any space. Initially there is no any volume in this side. This is left side our. This is right hand side. In left hand side, initial volume is, please remember that in your book their explanation is somewhat confusing. Okay, please consider this my explanation. Okay, here initial pressure of this left hand side chamber is P1 and volume is V1 and internal energy is U1, and you can see in right hand side initially there is no any space, any volume. So initially here volume is 0 in right hand side. However, left hand side the volume is V1. Okay, now imagine if the external pressure is P1. If the external pressure is P1, what will happen? If the external pressure is P1, nothing will happen, because internal pressure and external pressure will be same. Nothing will happen. However, we will introduce very small change, infinitesimal change. Atyanuka, infinitesimal or atyanuka, itamat kuda, dp amount of pressure I will introduce into this piston. Now the external pressure I increase by very tiny amount, infinitesimal change of dp. At that time the external pressure is slightly increased than internal pressure. Because of that, piston will move towards the chamber. After I adding this dp amount of tiny amount of pressure, this piston move towards the this porous plug. To this system, this left side chamber want to manage its pressure at constant at P1. So this left chamber want to manage its pressure, internal pressure as P1, not P1 plus dp. So to continue or to obtain constant pressure, this chamber will release some air particles into right hand side. මොකද කරන්නේ? මම මේක පද්ධතියේ මේක සමතුලිතවනේ තියෙන්නේ මුලින්ම. බාහිර පීඩනයේ අභ්‍යන්තර පීඩනයේ එක සමානයි. ඉතින් මේ පිස්ටන් එක මම ඇතුළට තල්ලු කරන්න ඕන නම් මොකද කරන්න ඕන? මම මේ එළියෙන් චූටි ප්‍රෙෂර් එකක් වැඩි කරන්න ඕන. අත්‍යානුක ප්‍රමාණයකින් dp ප්‍රමාණයක් වැඩි කරපු ගමන් මේක මෙහෙට තල්ලු වෙනවා. හැබැයි imagine this chambers contain ideal gases. Okay, initially I have to say that මේකේ තියෙන ideal gas පරිපූර්ණ වායු. හොඳේ, හරි. When I am increasing this pressure, piston will move towards this මේ porous සවිවර පේනුව දිහාවට piston එක තල්ලු කරනවා. මෙයා මොකද කරන්නේ? මේ left hand side chamber එක manage කරගන්න ඔයාගේ පීඩනය P එකේම තියාගන්න බලනවා. P එකේම තියාගන්න නම් අර වැඩියෙන් දීපු පීඩනයට සමාන ප්‍රමාණයක් නිදහස් කරන්න එපයි. එයා මොකද කරන්නේ? එයාගේ ඇතුලේ තියෙන gases මේ සවිවර පේනුව හරහා එහා පැත්තට තල්ලු කරලා දානවා. It will keep its constant as P1 by removing some excess air particles to the right hand side. Okay, now what will happen when I introduce dp? tiny amount of pressure, piston will move towards the porous plug. System will manage its pressure at P1 as a constant, but I introduce dP excess pressure to release that. This system will move its air particles, excess air particles, to right hand side to manage its to maintain its pressure at P1. එයාගේ පීඩනය P එකේම තියාගන්න ඕන නිසා අර වැඩි වෙන පීඩනයට සමගාමීව වායු අංශු ප්‍රමාණයක් දකුණු පැත්තට තල්ලු කරලා දෙනවා. Here your porous plug. Okay, now when I increase this piston, when it is moving towards the porous plug, some gases in this first chamber, left hand chamber, will goes to the second chamber, and imagine it will move its piston. First of all, I must say, when I introduce this P1 plus dP pressure into this left hand side, I will apply P2 pressure plus dP amount towards this right hand side piston. I will introduce first of all the pressure of both this system and external pressure was P1 and P1. I introduce dP amount of pressure, excess pressure. Because of that, piston will move towards the porous plug. At that time, this piston will try to move. However, I will introduce P2 plus dP pressure onto this piston. However, you have to remember that this P1 is larger than P2. Because of that, P1 is larger than P2 mean this syringe will, or this piston will move backwards because P1 is higher than P2. Okay. Now imagine at final time this left hand side piston will come to the end of its way, and here the final volume will be, final volume will be 0. Initial volume is V1, now piston came to the edge of its chamber, now volume is 0. However, here external pressure of right hand chamber is P2 plus dP. Its final volume will be V2, pressure will be P2, and internal energy will be U2. This internal pressure will be P2. Okay. However, don't think about this dP value because I introduce dP towards this piston, and against I introduce dP towards, in both pistons left and right both have dP, so they will be cancelled out, doesn't matter. The internal pressure dP will be the pressure of this right hand chamber is P2, initial pressure of this left hand side also P1, doesn't matter. This dP and dP will cancel out, so pressure will not be matter. Okay. However, P2 is less than P1, keep in mind. Because of that, this chamber moves towards the porous plug and this moves towards backwards. Okay. Okay. Now, this Joule-Thompson effect is known as isoenthalpic effect. Isoenthalpic means delta H is equal 0. This process is known as isoenthalpic process and ideal conditions. Okay. Now, what can I say about this? How can we calculate this? Okay. How can you calculate this? Let's we talk about the work. initially what will be the work during this piston moving towards this porous plug? There is a work. We know that there is a work W1 here and here another work W2. This piston move towards backwards or right hand side, it is W2. This piston move towards the porous plug, that is W1 work. There are two works. So shall we write down expressions for these works? Initially I will write down work for this left hand side chamber, that is meaning W1. Okay, common equation for expansion work, W equal minus Pex dV. Okay. Okay, what will be the external pressure of this first condition? P1 plus dP minus P1 plus dP. We know that external pressure always against the system. Always against means it is negative sign. However, what about the volume? dV. To get volume change, I told you in the first video also, when we are talking about change, we have to deduct lower initial volume by final volume. So what is the initial volume? Initial volume was V1. So it will deduct by final volume is 0. 0 minus V1. Because to get volume change delta V, we have to deduct final volume. We have to deduct initial volume by final volume. ආරම්භක එක්කෙනා අඩු කරන්න ඕන අවසාන එක්කෙනාගෙන්. එහෙම ගත්තොත් එහෙම අවසාන පරිමාව ඇවිල්ලා මෙතන බිඳුවයි, අවසානයේදී බිඳුවයිනේ මේක මෙහෙට තල්ලු වුණාම ආරම්භක පරිමාව V1යි. අඩු කරා. We can simplify this equation. W1 is equal minus, here now we will assume this dP. I told you this is very infinitesimal or අත්‍යානුක වෙනස් වීමක්, පුංචි වෙනස් වීමක් නේ. We assume this dP is negligible, 0. At that time I can simplify this equation. W1 equal minus P1 into 0 means 0. P1 into V1 is V1. Minus P1 V1 is the first work in left hand side. ඇයි එහෙම කරේ? මෙතන P එක දන්න dP, I assumed dP is negligible. dP is 0 and equation will be, should I write down that? Are you confused? I will write down. Okay, don't confuse. W1 equal, I assume dP is equal 0 because it is very small, infinitesimal, අත්‍යානුක වෙනස් වීමක්. එනිසා minus P1 into 0 minus V1. Minus P1 0 and here minus minus into minus will be positive, no? P1 V1. Okay. Okay, now here 0 and W1 will be P1 V1. It is positive. It's better I write down that because initially I was wrong. I put negative mark, but it should be positive like this. Okay, එක ධන වෙන්න ඕන. කොහොමද? මෙතන ඍණ ලකුණනේ ළමයි තියෙන්නේ. ඍණ P එක ඍණ V එකෙන් වැඩි වුණාම ධන වෙන්න ඕන. දැන් හරි, W1 is equal positive V1 V1. Okay. Now what about the W2? Right hand side, what happened? According to that, the pressure is minus Pex dV, its expansion work, minus P. Now Pex external pressure is, its external pressure is dP plus P2, P2 plus dP. And volume change, what is volume change here? Initial volume is 0, final volume is V2. Final volume minus initial volume is V2 minus 0, V2 minus 0. Okay, let's simplify. I assume dP is negligible, 0, and minus P into V2 minus 0 equal minus P V2 minus 0 is 0. So my answer will be here P2, I forgot again, I'm sleepy, I feel sorry, W2 is equal P2 V2 minus P2 V2. This is the work done in second chamber, right hand chamber. Now what is the total work done in this process? In both process, the total work is equal W1 plus W2. Okay, W1 mean P1 V1 plus W2 mean minus P2 V2. W equal P1 V1 minus P2 V2. This is the equation for total work throughout this whole process. හරි, දැන් මේක අපි ගත්තා. මේකට එනකන් ඔයාලට තේරෙනවනේ. පළවෙනි චේම්බර් එකේ කරපු කාර්යය බැලුවා, දෙවෙනි චේම්බර් එකේ කරපු කාර්යයට ප්‍රකාශන දෙකක් ගත්තා. ඒකලා සම්පූර්ණ කාර්යයට මේ දෙන්නගේ එකතුව ගත්තා. මෙහෙම සමීකරණ දෙකක් අපි ගත්තා. හරි. Now I will erase these things. I need more space for further calculations. Okay, I imagine you may write down everything. Okay, now you know expression for internal energy. Delta U is equal Q plus W, and you know what is the change of internal energy. Here U1 and U2 know. What is the change of internal energy throughout this process? Delta U is equal, we told you initially, this internal energy also a thermodynamic property or state property. It depends on the initial state and final state. So to get the change, I reduced final U, final internal energy by initial internal energy. So delta U is equal, final mean U2 minus U1. This is the expression for internal energy in this process. Okay, we got this equation also. Now according to first law of thermodynamics, delta U is equal, here I consider delta dq, du equal dq plus dw. Here initially I told you this cylinder is frictionless and it is thermal insulation. Tapa parivarakayak කියලා කිව්වා, thermal insulated. So dq will be 0 here in this process. So du is equal, dq is 0 because this cylinder is insulated, thermal insulated. Energy will not get out or get in, so it is dq is 0, and here dw. Okay, I finalize this equation. Okay, next, what is the relationship between enthalpy and internal energy? There is a relationship between enthalpy and internal energy. H equal U plus PV. Okay, this is expression for enthalpy. Okay, H equals U plus PV, common expression for enthalpy and the relationship between enthalpy and internal energy. Keep this in your mind. It is useful equation for the calculations. However, here internal energy, first law simplified as this, du is equal to dw. So we can write down expression combining with this. Du is equal, instead of the dw, I will write down this expression, d P1 V1 minus P2 V2. Okay, change, instead of the dw I substitute this. Okay, okay. Now how can we simplify these equations? So here, to change of internal energy, we can get this equation. Instead of this du, here imagine this is du, u2 minus u1 equal d P1 V1 minus P2 V2. We got two expressions. Okay, one equation. So we can rearrange this equation. Here 2, 2, 2. We get same numbers into same side. So U2 plus, for a while we will forget this d for a while. Okay, so at that time I can rearrange this equation. U2 plus P2 V2 equal U1 plus P1 V1. Okay, now got this equation. Now it is familiar. How? H equal U plus PV. Here U plus PV. So this may be 1 mean H1, 2 mean H2, because H, this is expression for enthalpy, this U and PV. So final results will be H1 is equal H2. That means this is an isoenthalpic process. We proved that. These are the common equations. I think it is not doubtful. You may understand everything. According to your book, which especially in English medium book, somewhat confusing, because there are some points should added, this dp and likewise. It's somewhat confusing, but this method is very easy for you. Okay, this is the final conclusion. However, there are other calculations further about this Joule-Thompson effect. Okay, let's move. Now let's write down an expression for H, enthalpy. In last video I discussed about this also. H is a function of P and T. As exact differential and partial differentials, we can write down this equation as අපි කියවනේ මේක ලියන්න පුළුවන් ක්‍රමයක් තියෙනයි කියලා. dH is equal da by h divided by da p t dp plus da h divided by da p da t p into da dt. Okay, this expression we can obtain by simplifying this exact differential and partial differential equations. මේක අපි සුළු කරගන්න පුළුවන්. හරි. ඊට පස්සේ මම පොදු equation එකක් ගන්න අපි දන්න දෙයක්. Cp is equal Cp කියන්නේ කවුද ළමයි? dqp divided by dt. We know that Cp is equal dqp divided by dt. Okay. Now this dqp, we know that dqp කියන්නේ කවුද ළමයි? Cp is equal dqp කියන්නේ සමපීඩන උෂ්ණතාප වෙනස් වීම. Heat change, exchange in an isobaric. That means dH, enthalpy over dt. Okay. So here isobaric process. So in this equation we can see that expression dH over dt over p. This deba also d but to indicate partial differentials we include this deba sign, but deba is equal to d. This expression is equal to this expression, so we can simplify this equation. dH is equal deba h divided by deba p t dp plus, instead of this part I will introduce Cp dt. Okay, I simplified this equation. Okay, now we know that in this Joule-Thompson we call this phenomena Joule-Thompson expansion. මේකට Joule-Thompson ප්‍රසාරණය කියලා තමයි මේ ක්‍රියාවලියට කියන්නේ. Joule-Thompson expansion is isoenthalpic process. dH is equal 0. So here dH will be 0. 0 into is equal deba h divided by deba p t dp plus Cp dt. Okay, we simplified this equation according to this assumption. dH equals 0. Actually not assumption, we proved that in previous calculations. Okay. Now I will rearrange this equation. I will move this deba h part to left side. I write down it. So here positive, now it's go to left side, it will be negative. I will use red color. Negative deba h divided by deba p t dp is equal Cp dt. Okay, now we got this equation, and if we divide this equation by dp, we will divide this equation by dp, and in isoenthalpic conditions, that means delta H equal enthalpy is constant. So we divide this equation by dp when enthalpy is constant. Okay, how can we divide? Deba minus deba h deba pt, this expression can't divide because it's already divided. However, this dp is alone. dp divided by dp at enthalpy is constant. Here enthalpy is constant is equal Cp dt. I will divide it by dp. Here Cp is constant. I put it out, and dt divided by dp, and enthalpy is constant. I arrange this equation. Okay. Now dp divided by dp into h is constant mean 1. මේ කියන්නේ 1යි. අපි I will erase upper part. Minus deba h deba p t. Here this part is 1. I will not indicate 1. Is equal to Cp. This dt and dp part I will write as deba. Deba T divided by deba P. H is constant. Okay. Now, according to the theory, this deba T divided by deba P constant H is equal to a coefficient deba T, and they given in our book also in theoretically deba T divided by deba P constant H is equal to a coefficient called mu Joule-Thompson. මේක Joule-Thompson සංගුණකය කියලා කියනවා මෙන්න මේ part එකට. So by substituting that mu Joule-Thompson coefficient into this equation minus deba H deba P T equal Cp mu Joule-Thompson coefficient. Now this is the expression for Joule-Thompson coefficient deba T divided by deba P H. This is the common expression for Joule-Thompson. You have to remember that. And another expression we can made up from this equation minus deba H divided by deba P, here T, or 1 over Cp equal mu Joule-Thompson. Now we got two different expressions for Joule-Thompson coefficient. This and this. Okay. Now these are the things you have to remember. However, this is a summary. Depending on the value of this mu Joule-Thompson coefficient, we can say whether the system is cooling or it is increasing temperature or it is not changing. Okay. Here, if the mu Joule-Thompson, this Joule-Thompson coefficient, if it is 0, that means no temperature change. That means dt equals 0. If mu Joule-Thompson equals 0, that means dt equals 0. Here, this condition apply for ideal gases. In ideal gases, this mu Joule-Thompson coefficient is 0. Okay. Now the second thing, if the Joule-Thompson coefficient is negative, that means the temperature will increasing in the system. Okay. If the Joule-Thompson coefficient is positive, that means it is temperature decreasing, mean cold. This is hot, this is cold. Okay. So these are the things you have to remember. If mu Joule-Thompson coefficient is 0, that means it is ideal gas and temperature will not change. If the Joule-Thompson coefficient is negative, the system is it's increasing temperature. It is get hot. If the Joule-Thompson coefficient is positive, the system is cooling. It is cold. Temperature is decreasing. Those things you have to remember related to this Joule-Thompson effect. Okay. I finish everything. I will give very brief introduction to heat engine, and I will end up this advanced thermodynamics session. Okay. In heat engine theory, how can we explain that? There is a hot reservoir උෂ්ණත්වය වැඩි තැනක් තියෙනවා, source of energy, higher temperature, and there is a low temperature source also, temperature is lower. In between them we have our system. Okay, from this higher temperature reservoir, මේ උෂ්ණත්වය වැඩි කෙනා means its Q is also increased. Higher temperature mean its heat also higher. Lower temperature mean heat also lower. However, this higher temperature reservoir, higher heat energy reservoir will transfer its energy to the system. Because of this gaining energy, system will do works. This will be mechanical work. Because of this providing heat, it will expand. This expansion, because of that, it will do mechanical works. No, so every heat given by this hot reservoir will not generate mechanical work. Some of this will goes to environment. So if you consider this is QH, this energy given by the hot reservoir is QH, and the mechanical work done by this gaining energy, if it is W, and unused energy will be, they will exposed to environment without any work, that will be QC. Okay, so what will be this work when we get this combination of this process? We can write down an expression for work done. Here work done is equal to QH minus QC. This is the expression for work. මොකද උනේ මේ වැඩි තාපයක් තියෙන කෙනාගෙන් තාපය සිස්ටම් එකට දෙනකොට එයා එක්ස්පෑන්ඩ් වෙලා ඒකෙන් පරිසරය මත කාර්යයක් කරනවා. ඉතින් එන්ජින් එකේදී කරන්නේ ඒකනේ. එන්ජින් එකේදී කරන්නේ තාප එන්ජිමේදී කරන්නේ වැඩි තාපයක් තියෙන කෙනාගෙන් ශක්තිය අරගෙන පද්ධතිය එක්ස්පෑන්ඩ් වෙලා පරිමාව වැඩි කරගෙන මේ වගේ කාර්යයක් කරනවා පරිසරයම. ඒක තමයි අපි ප්‍රයෝජනෙට ගන්නෙ. නමුත් මේ දෙන තාපය සම්පූර්ණයෙන්ම වර්ක් නැත්නම් කාර්යයක් බවට පත් වෙන්නේ නැහැ. කොටසක් හානි වෙනවා. මොකද එන්ජින් එකත් රත් වෙනවානේ. එතකොට කොටසක් තාපයේ විදිහට අපත යනවා. ඒ අපත යන තාපය QC, ලබා දෙන තාපය QH, කාර්යයන් විදිහට ගන්නේ W නම් මේ දෙන්නගේ වෙනස ඉන්නේ කාර්යයෙන්නේ W සමානයි දෙන කෙනයි හානි වෙන කෙනයි අතර වෙනසින් අපිට ගන්න පුළුවන් කාර්යය කොච්චරක් කරාද කියලා. Okay. Now what is the efficient of this engine? Engine එකේ efficient එක මොකක්ද? Efficient mean given energy is QH, work done was W, and into 100, this is the efficient of this engine. engine මේ කාර්යක්ෂමතාවය කොහොමද කියලා අහුවොත් එහෙනම් මොකද කියන්නේ? ලබා දීපු තාප ප්‍රමාණය, ආරම්භක තාප ප්‍රමාණය සම්පූර්ණ QH, ඒකෙන් ප්‍රයෝජනෙට සඳහා යොදාගත්තේ W ප්‍රමාණයක්. එහෙනම් ඒකේ 100ට කොච්චරද කියලා බලලා අපිට කියන්න පුළුවන් මේකේ කාර්යක්ෂමතාවය කොච්චරද කියලා. Okay. Finally, what will be the this power of this system engine? Engine මේ power එක කොහොමද කියන්නේ? power of this engine. engine මේ බලය කොහොමද අපි දෙන්නේ? Power will be work divided by time in seconds. Okay. So this will be given by watt. Power will be given by watt. So here work is joule, joule divided by seconds. So we get the power of this engine. Okay. So this is the very brief summary. You have to go through the book for this process. It's very simple, this engines theory. So however, this is the very small conclusion. You have to go through the book also. Okay, this is the end of this thermodynamics advanced session. So I think you got you may got some at least small knowledge from this video series. So if you get anything from this video, please leave a comment, and please subscribe my channel, and please share this video, and please stay with me because I will upload so many videos about your university level, your first year, second year and third year. So subscribe my channel and keep alert with me. So thank you for watching.